Here's the solution to homework set number 2 for ECE 321 Analog Electronics. This homework set covers temperature sensors, audio and strain sensors, calibration, and noise. Now the first problem looks at temperature sensor, specifically a thermistor. Now a thermistor is a resistor whose temperature varies with resistance. So as temperature goes up, the resistance goes down. One problem with the thermistors is they're nonlinear. To fix that, I can add a linearizing circuit. What that is I take my thermistor, add two resistors to it, one in series, one in parallel. So this is your RA, RB. If you do it right, this will be roughly linear over a small range. So problem 1 is find RA and RB so that you're roughly linear between 0 and 15 degrees Celsius, meaning at 15, the resistance is halfway between the two endpoints. Now a problem with this is one solution is RA equals infinity. That's not useful, but it is linear. A second solution is RB equals 0. Again, not useful, but it is linear. Find a solution where RA is not infinity, RB isn't 0. And the challenge, here what I tried is I just said RA equals RB. What can you do under that constraint? So again, at 0, 15, 30 degrees Celsius, calculate the resistance. Find the total resistance, that's your R1, R2 over R1 plus R2, an equation for two resistors in parallel. My error is when I do that, you've got this curve, I've got a straight line. At the midpoint, what's that distance? That's the error. Return the sum squared error and try to minimize j, hopefully make it 0. Once I define my function, I can minimize it in MATLAB. So I'm going to use fmin search, minimize this function. There's my initial guess, let it go. And after a couple seconds, MATLAB kicked back this answer, and there's my sum squared error. Pretty close to 0, so that looks like a valid solution. So it looks like one solution is RA equals RB is 592.6961 ohms. To check that, let's calculate the resistance between 0 and 30 degrees Celsius with 3,000 points, just to show off. Calculate the resistance of the thermistor at all 3,000 points, calculate the circuit resistance at all 3,000 points, and plot them. The temperature versus resistance in blue, and just draw the endpoints in red. What that looks like is the two endpoints are connected in red. The blue line, it doesn't exactly follow it, but I forced it to match at the midpoint and the two endpoints. So it's actually not too bad. So that's one solution. There are others. Once I get that circuit, I can now build a circuit to amplify and drive the output to 0 to 5 volts as temperature goes between 0 and 30 degrees Celsius. The first step is pick your favorite resistor up here for voltage divider. I chose a 1K. Here's my linearizing circuit. Once I do that, I have a voltage at 0 and 30 degrees Celsius. At 0, I want the output to be 0. At 30 Celsius, I want that to be 5 volts. So to do that, I calculate what's the impedance at 0 degrees Celsius from the voltage divider. X is 3.39 volts, Y should be 0. At 30 degrees Celsius, X is 2.93 volts, Y should be 10. I guess it went 10 volts. So as X goes down, Y goes up. So connect to the minus input. That's over here. When X is 3.39, Y is 0. So to make the output 0, these two match. So my offset is 3.39 volts. And the gain I need, the output changes by 10 volts as the input changes by something, gives a gain of 21.79. Make these resistors 21.79 to 1. So this circuit should output 0 volts at 0 degrees Celsius, 10 volts at 30 degrees Celsius. And it'll be mostly linear. To calculate it, again, take 3,000 points between 0 and 30 degrees Celsius. Here's the voltage by voltage division. Here's the output. It's a gain times A minus B. And then plot it. The data in blue, the endpoints in red. The endpoint, the red line, it should be a straight line. That's what I want. It's not quite a straight line because the voltage divider is nonlinear, so it's a little bit different. And actually would be slightly better design is instead of choosing the linearizing circuit to make the resistance linear, I should choose it to make the voltage linear. That's not what was asked for, but that'd be actually better to do it. But you still wind up with a pretty close to a straight line, voltage between 0 degrees and 30 degrees Celsius. Problem 3. Another thing I can do is if I use a 555 timer, I can have frequency vary with temperature. So here's my linearizing circuit. It makes the resistance linear versus temperature between 0 and 30. Here's my 555 timer. I picked this to be 1K because I like 1K resistors. This is calculated. Pick that so it's 500 Hertz at 10 degrees Celsius. So the period is R1 plus 2 times R2, or 2 times Z times C times log of 2. At 10 degrees Celsius, Z is 482 ohms. If R1 is 1,000 ohms, I have one equation, one unknown, solve for C. C should be 1.468 microfarads. I can now calculate the period or frequency versus temperature. Here's C, here's the period, R1 plus 2 times R2 times C times log of 2 at all 3,000 points between 0 and 30 degrees Celsius. Frequency is 1 over period. Plot temperature versus frequency in blue, the endpoints in red, and here's what you get. Not quite linear because Hertz is 1 over period. That's not linear. So the period's actually linear in temperature. 1 over period is not. So again, if I use the period instead, it would be linear. If I wanted the frequency to be linear, I would probably redesign the linearizing circuit so this guy is linear. The point in the middle passes through the midpoint. But it's still not bad. So there, if I measure frequency, I can tell you temperature. Problem 4 looks at calibration. If I skip that linearizing circuit and just use the thermistor all by its lonesome, here I've got a thermistor, here's a 1K resistor, and here's 10 volts. This voltage here, I'll call V, completely original name. If I plot the voltage versus temperature, it's not going to be linear. So I can do that. Here's temperature, here's resistance of the thermistor, and call that R. Here's the voltage. So I'm going to get some curve. And it's going to do something kind of like this. Draw a straight line approximation to it. To do that using least squares, I pick a basis. Here my basis is voltage and 1. One way to get the number 1 is V to the 0 power. Anything to the 0 power is 1. That just gets the dimensions right. Now do least squares. Least squares is the inverse of B transpose B times B transpose times my output, which is temperature. And here's my curve fit. So my curve fit is temperature is roughly minus 9.15 times voltage plus 70. And if I plot that, here's a mistake. Plot voltage versus temperature in blue, voltage versus curve fit in red. That's what it looks like. So the blue line is the actual data. The red line is my straight line curve fit. You can kind of see it's not too bad. So if I know voltage, I can tell you what the temperature is. And the maximum error is 0.5 degrees Celsius. That's probably right about here. That's one way to do it. If I do it a cubic curve fit, it's really not a whole lot different. Just change the basis to be V cubed, V squared, V in 1. Recalculate A using least squares, and I now have minus 0.14 V cubed plus 2.5 V squared minus 23V plus 96. And if I plot voltage versus temperature, what it really is, voltage versus curve fit in red, that matches really, really well. And the maximum error is 0.02 degrees Celsius. That's calibration. Take something that I know, voltage, and calculate what I want to know, temperature, so that with that curve fit, if I know what the voltage is, I can tell you what the temperature is. And the calibration error is only off by 0.02 degrees Celsius. Problem 6 shifts gears and goes into strain gauges. Strain gauge measures how much a metal stretches or contracts as you bend it. So if I take a bathroom scale, push on it by 200 pounds, and there's a little 1 millimeter beam it deflects by 6 millimeters. How much did the outside edge stretch? That's the strain. And how much does resistance change if I could put a strain sensor on there and design a circuit to output 0 to 10 volts as the force goes 0 to 200 pounds? The first step is to find the strain. This is a circle. So again, I've got a circle with radius r. This distance is 6. This is r minus 6. And this is 50 millimeters. I've got a right triangle. So r squared is 50 squared plus r minus 6 squared. Solve for r. R is 211.33 millimeters. So essentially I have concentric circles. The center line is 211.33 millimeters. The outer edge is going to be plus 0.5 millimeters. Inner edge is minus 0.5 millimeters. If the center line is neutral strain, then the outer edge is stretched. The circumference of a circle is pi d. So as the diameter increases, the circumference increases. The relative strain is it increased by 0.5 millimeters at a radius of 211. So that's the strain. Half the thickness over the radius. The strain is 0.0023 on the outer edge. The inner edge will be minus 0.0023. It compresses. If I put a strain sensor on the outer edge and it has this resistance versus strain, plug in 0.0023 strain, and the resistance becomes 120.6 ohms. Not a huge difference, but it is there. To design a circuit to convert that to 0 to 10 volts, what I'll do is form a voltage divider. At 0 strain, this is 120 ohms. At 200 pounds force, this is 120 point, I forgot, 6075. 6075 ohms. I want to have that go to 0 volts. I want to have this go to 10 volts. So the first step is where's my calculations? There they are. At 0 pounds force, I made that 10 volts. At 0 pounds force, this is 5 volts. At 200 pounds force, it is 5.01 volt. I want the output, so this goes 5 volts to 5.01 volts. Again, you need more decimal points. I kept all the decimal points in the calculations, but just for limiting what I'm writing. When the input is 5 volts, I want the output to be 0. 5 volts. So there's my offset. The gain I want is the output changes by 10 volts as the input changes by 0.012 volts. I need a gain of 792. So pick that to be 792 to 1 ratio. And I now have an amplifier that'll convert output 0 volts at 0 pounds and 10 volts at 200 pounds force. That's how a bathroom scale works. And typical strain gauges, you need a lot of amplification. And kind of one note, you actually can do a little bit less. Here I just have a single strain gauge on the outer side, and I'll need to temperature compensate it. If I have 2 strain gauges, one on the outside, one on the inside, that'll do temperature compensation. Plus, I get double the voltage change, because when A goes up, B goes down, and I'll need a gain of half that. If I generate this 5 volts by going 10 volts to ground through two 120 ohm resistors, that's one way to generate 5 volts. If I make this 2 other sets of strain gauges, so on one side I have A and B, on the other side I flip them. I have A and B. As this side goes up, that minus goes down. As plus goes down, minus goes up. I'll have 4 times the sensitivity, so I'll need 1/4 of the gain, but cost 4 times as much because I now have 4 strain gauges. So that's the strain gauge problem. Problem 7 looks at trying to transmit sound on a light beam. Suppose this resistor was 1000 ohms and varied by 50 ohms. What are the voltages at V1, V2, and V3? Well, at V1, it's nominally 2.5 volts. At 1050 ohms, the peak I'll be 2.56 volts. So it's doing this. I'll have a sine wave. The center is 2.5 volts. The peak is 2.56, so that's 0.06 volts. Peak, and that's also 0.06 volts. So this has a DC and an AC term. DC is 2.5 volts. The AC is 0.06 volts peak, or 0.12 volts peak to peak. Pick your favorite unit. So there's my peak voltage. This is a voltage divider. That's 100 kiloohms at 1 kilohertz. This is minus J1592 ohms. Basically 0 relative to 100 kiloohms. So V2 is almost the same as V1. If you split hairs, actually this is slightly different. Instead of 60.98 millivolts, this is 60.97 millivolts. You lose a little bit across the capacitor, not much. Then the amplifier. This will amplify the AC signal, amplify the signal. There is no DC component. So it amplifies the AC component by 4. So at V3, I have no DC and 182 millivolts peak to peak. Or correction, 182.9 millivolts peak. AC, got to get the units right. This is a peak voltage. And then problem 8 and 9, that was your choice. Build an amplifier to amplify a microphone or to transmit sound on a light beam and demonstrate it. So that is homework set number 2 for ECE 321, Analog Electronics.